Dear student, colleagues, and all the viewers were watching live program uh, from this Facebook page, Live Physics Adda. I'd like to welcome all of you to my webinar. Good afternoon to all here in Bangladesh, and good morning to all those who are watching this program live from UK. So our today's guest is Dr. Teppei Katori sir. So he's already have connected with us. So good morning, sir.
Good morning.
Okay. So welcome to my webinar and welcome to Bangladesh through online. I think this is maybe your first webinar with any Bangladeshi teacher on student. Is it?
Yeah.
Okay, then and this is also a special day for us because we are actually making history because today our department is going to arrange a collaboration webinar with one of the best Neutrino physicists from UK, and actually I feel proud, and I'd like to say thank you from on the behalf of Department of Physics, Patna University of Science and Technology. So we are passing a bad time due to the corona pandemic, and all the institutions have shut down due to corona pandemic, and so it's very difficult for us to interact with students. So our department have taken some initiative to continue this educational program by arranging some online classes, webinar, and online seminar. So you have already came to know that in those webinar and seminar, the scientists from different countries came to join as a speaker. So our today's speaker is Dr. Teppei Katori from UK, and you have already came to know that today's webinar title is Constraint on the Matter-Antimatter Symmetry Violating Phase in Neutrino Oscillation. So I have divided the webinar in three different parts. First, I'd like to introduce our speaker with all of you. Then there is a discussion. There is a time where our speaker will deliver his speech, and finally we have a discussion session. In that time, anybody can join us and ask question, or you can ask question through Facebook by commenting. So Dr. Teppei Katori, currently working as an associate professor, Department of Physics, King's College London. He is an experimental physicist, and he is one of the best Neutrino physicists in the world. And he completed his bachelor degree in physics from Tokyo Institute of Technology, Japan. And then he completed his PhD degree from Indiana University, Bloomington, USA. And in his PhD work, he worked on neutrino cross-section measurement and new physics search in the mini bone experiment at the Fermi Lab, USA. And he done his first postdoc at MIT, USA. After that, he joined as an assistant professor at Queen Mary University of London, UK. And he also got some awards from different organizations. Currently, he's working as an associate professor at King's College London, UK, and the chair of the Institute of Physics Astroparticle Physics Group. He works on several neutrino experiments, including T2K, Super-Kamiokande, and Hyper-Kamiokande experiment. Those experiments are from Japan, and also Ice Cube Neutrino Observatory, Antarctica. So if you see the ResearchGate ID of Dr. Teppei Katori, you can get his ResearchGate number is very good, 35.15. And if you see the Google Scholar ID, you become astonished by seeing the citation number. It's more than 10,000, and I actually personally feel proud to get him as a main speaker of today's webinar. So before going to his piece, I'd like to say something about matter-antimatter and neutrino, because some students who are in first year or second year, they might be benefited for this. So what is matter? So we know the matter is a substance that has mass and occupies space and having volume. So everything in the universe is made up with matter. matter can have different states like solid, liquid, gas, plasma, Bose-Einstein condensate, fermionic condensate, quark-gluon plasma. All the matter are made of electron quarks and very occasionally other lepton. So if we see antimatter, matter is made of particle. On the other hand, antimatter made of antiparticle. So every particle has corresponding antiparticle with corresponding mass and spin. But some non-zero quantum number like electric charge, color charge, flavor, electron number, tau number, baryon number, those have opposite value. If we see some example for proton and antiproton, so you can see in proton, the proton is made with 3 quarks, 2 ups and 1 down. And in antiproton, it's an antimatter of proton. So 2 anti-up quarks and 1 anti-down quarks. So particle antiparticle relation. So we have every particle has antiparticle. We have already told. So if you see the quarks, we have a 6 quark as a particle and their antiparticle. So we have a 6 up, down, charm, strange, top, and bottom, and their antiparticle, anti-up, anti-down, anti-charm, anti-strange, anti-top, and anti-bottom. For neutrino, we have a 3 neutrino, electron neutrino, muon neutrino, tau neutrino, and their antiparticle, anti-electron neutrino, anti-muon neutrino, anti-tau neutrino. For muon, there is a antiparticle, anti-muon. For tau, antiparticle is anti-tau, and for electron, antiparticle is positron. For matter, we have already told about proton. So we need 3 quarks to make a proton, and antiquark also need 3 antiquarks. For neutron, we need 1 up quark and 2 down quarks, and for anti-neutron, we need 1 anti-up and 2 anti-down quarks. If we see for nucleus, if we consider 4 helium nucleus, we can see there is 2 proton and 1 neutron. And for anti-nucleus, we have 2 antiproton and 2 anti-neutron. For atom, if we consider hydrogen atom, we have 1 proton and 1 electron. For anti-hydrogen atom, we have a antiproton and positron. And we have also molecule. For molecule, if we take water, so we have 2 hydrogen atom and 1 oxygen atom for matter. And for anti-molecule, we have 2 anti-hydrogen atom and 1 anti-oxygen. So what will happen when these two collide? So when matter and antimatter collide, they will annihilate, and most of the mass converted into energy, especially gamma ray. And conversely, when sufficient energy is available to provide mass and energy, a particle and antiparticle can be produced. Here, the proton and antiparticle they collision, and you can see in this picture, electron and positron and gamma ray has become. So now somebody may ask you, what is a neutrino? Neutrino is a elementary particle, and neutrinos are electrically neutral lepton. So they are fermion, and they undergoes weak interaction, and their spin is half integer. They are one of the fundamental particles which are responsible for creating the universe. A neutrino is also known as a subatomic particle like electron, but the charge is 0 and mass is very tiny. And we can get neutrino in 3 flavors: electron family, muon family, and tau family. So sources of neutrino, there are 2 different sources. One is natural and another is artificial. As a natural source, we have atmospheric neutrino, solar neutrino, supernova neutrino, high energy neutrinos, Big Bang relic neutrino, and neutrino from center of Earth. And for artificial neutrinos, we have neutrino from accelerator and reactor. So different types of neutrino, we have already told that the neutrino can get 3 different family: electron, neutrino, muon, and tau, and their antiparticle: anti-electron neutrino, anti-muon, and anti-tau. Properties: extremely teeny, their mass is very teeny. They do not interact with strong force. They do not interact with electromagnetic force. They just interact with weak interaction and gravitation. But gravitation depends on mass. As neutrino mass is very teeny, so gravitational effect is negligible. And as they are fermion, their spin is half and charge is 0. For neutrino detection, so neutrino have extremely small interaction with matter, so it's very difficult to detect. But we can detect their existence by 2 main ways. We can detect neutrino. One is charge current interaction, another is neutral current interaction. So in charge current interaction, neutrinos are converted into another equivalent charge particle. For example, inverse beta decay. Here you can see a antineutrino interact with proton and become positron and electron. And on the other hand, in neutral current interaction, the neutrino remains neutrino after interaction. So here you can see a neutron electron elastic scattering and neutrino deuteron scattering. The first neutrino was observed for the first time by Fred Raines and Clyde Cowan with the help of charge current interaction 1956 in the time of measuring anti-electron neutrinos via the inverse beta decay interaction in the water tank. So thanks. Now time to go to our main speaker, today's main speaker. So, sir, you can start your session now.
All right, so let me try to share my screen. We tested yesterday, so it should work.
Yeah, of course. I think
let's
so.
see. Share screen.
Is it okay?
It's the entire screen.
Not connect. Oh, okay, maybe now.
Do you see my screen?
Yeah, now it's coming. Next time maybe.
Okay, so I will start, and then so please let me know if something go wrong.
Not yet. Okay, I think
All
you
right.
can start. Yeah, it's come.
Great.
So we can.
Okay, so thank you for invitation, and okay, great. So thank you for inviting me for this webinar series. So my name is Teppei Katori. I'm from King's College London, and so today's talk is this. The title is Constraint on the Matter-Antimatter Symmetry Breaking Phase in the Neutrino Oscillations. So this is a recent result, and then we are even make a cover of this Nature journal, which is it's a very big deal. So, and it's a very nice subtitle, Mirror Cracked. So that's the topic of talk, and I want to have again repeat a little bit about what is neutrinos basically. So I want to talk a little bit, and then I want to explain what is the neutrino oscillation experiment is, especially this T2K experiment we are working on. If you want to measure neutrino oscillations, you need two things. The one is a neutrino beam. So I want to explain how to make a neutrino beam. And then you want to measure neutrinos. So you need a neutrino detector. And I want to explain how to measure neutrinos. And a little bit, I want to talk about neutrino interaction physics. That's a kind of topics me and the Pretam is working on. So I want to have a small review of neutrino interaction physics, and then I move on our result, and then our future plan, which is SKGD, T2K upgrade, and Hyper-Kamiokande, and a conclusion. Okay. So neutrino physics is very flourish. It was not very popular years ago, but now it's amazing progress for many aspects. And then the Nobel Prize came a few years ago. So it's a very popular now.
Yeah.
And then this left side, this is called Breakthrough Prize. It's coming from the Facebook actually, but
yeah.
So it's the main experiment won this too. So it's very popular. So let's go through slightly before I'm moving on my next talk. So Pretam already introduced standard model, but standard model again, it's an elementary particles of the universe. So in principle, we can predict everything in the universe from the standard model. The reality is not. But so let's all go through. So there are 6 quarks, 6 leptons, and 3 force carriers. and the gold particle Higgs boson. So there are 6 quarks, but the important one is the first 2 quarks, up quark and down quark, because they make proton and neutron. And the leptons, so there are 3 charged leptons, and again, the important one is electrons, because up quark and down quark makes nucleus, and the nucleus and the electron makes atom. So everything in the universe is only these 3 particles, and the rest of the quark, there are another 4 quarks and another 2 charged leptons. They don't matter, or we don't know why they exist. So that's my first introduction. And then neutrinos. So there are 3 neutrinos: electron neutrino, muon neutrino, and tau neutrino, which is today's topics. The force carrier, there are 4 types of force, but 3 of them are in the standard model: strong force and electromagnetic force mediated by photon, and weak boson mediated by the weak boson mediated weak force. And the neutrino only interact with weak force, which means neutrino only exchange weak bosons. So that's the reason why interaction of neutrino is weak, or it doesn't interact very often. The weakest force in the nature is gravity, actually, even though we feel gravity very well because the gravity of the Earth is strong, but gravity of 2 protons is pretty weak. And gravity doesn't fit in the standard model, and so we don't talk. In general, we don't talk gravity in the particle physics. Finally, there's the gold particle Higgs bosons, which gives a mass to the particle and discovered in 2012. So it's a bit irony, because I just said we don't talk about gravity, but there's a particle which gives the mass. So clearly mass and gravity are not related too strongly, or we don't know how they're related still. So the summary of the standard model is that, so we discovered all the particle. We discovered all predicted particle in the standard model, but there are so many mysteries. The one additional mystery is the baryon asymmetry of the universe. Because we believe everything in the universe is made by Big Bang. So Big Bang generates particle, which is a matter, and the antiparticle, which is an antimatter. And there should be a same number. But the current universe has a slight asymmetry, and there are more particles than the antiparticle. So why do we know this? Well, because we are all made by matter. So we know there's no antimatter. And observation also suggests there's no star made by antimatter. So universe is basically only matter. So Sakharov proposed this could be a possibility if the matter-anti-symmetry is broken. Then matter-anti-symmetry is called CP symmetry. So this CP violation, if CP violation exists in nature, we could have a more matter. So people are looking for CP violation many years. And we discovered a long time ago, 50 years ago, there is a CP violation in quarks, but it is very small. So probably this CP violation can't generate this matter-antimatter asymmetry in the universe. So maybe we have other CP violation. For example, so quark violates CP. So how about leptons? Can lepton violate CP symmetry? So that's the topics of this talk. Before moving on that, I have a few more about neutrinos. So neutrinos are interacting only with weak force. So that means it's very difficult to interact, or a neutrino is very difficult to stop. So that's why neutrino is often called like a ghost particle. So let's imagine how you stop the particle. For example, alpha. So alpha is a nuclei of helium. So if you have a paper, you can block most of the alphas. And beta particle, which is electron. So if you have a paper, maybe some of beta penetrate. But if you have a sheet of a metal, like a copper, then you can stop all beta. The gamma is the hardest one to stop. So because gamma even penetrates most of the metal. But if you have a kind of brick or chunk of lead, you can stop gamma ray. So now question to neutrinos. How do you stop neutrinos? So lead is good. So lead is a good material to stop neutrinos. So let's prepare a lot of lead so that you can stop neutrinos. And it turned out you need almost the volume of 1 light year thickness of lead. So if you put the lead brick from the Earth all the way, passing through Pluto and on the outside of the solar system, then finally you can stop neutrinos. And obviously we can't do this for experiments. So how do you measure it? Well, so that's on average. So on average, you need a 1 light year length of lead to stop it. So if the neutrino pass through 1 light year in the material, it may stop. But sometimes neutrino hit because interaction is it's a probability. So some neutrino interact much earlier because you have some distribution, and some neutrino is just statistically likely to interact. So what you have to do is you have to make a big detector, and you try to see every tiny interactions and wait a long time, because there are lots of neutrinos, so sometimes they interact. So that's an interaction about neutrinos. But now I'm moving on quantum mechanics to talk about neutrino oscillation. So neutrino obeys quantum mechanics, which is true for every fundamental particles. So neutrino is a wave and a particle, which is a wave-particle duality. Also, this is an example of the two waves. So left side is so-called plane wave. So plane wave is a constant frequency, so it looks like a wave. And the right side, it's called a wave packet. So if you have a superposition of plane wave with a different frequency, you can make the wave more localized in the space. That is called a wave packet. And these waves are more likely a particle. So that's how you explain the particle with a wave. So now you know the particle is a wave. And since neutrino obey quantum mechanics, so that's also there's a situation like a Schrödinger's cat. And I skip detail, but so basically the state of neutrinos are not well defined in space and time. So let me explain what the Schrödinger's cat is. So there's a cat, and there's a poison release device, and both are in the box. And there's a radioactive material in the box. So there are three things: cat, poison release device, and radioactive materials. Yeah. And there's a 50% chance this radioactive material decay so that it triggers the device and release poison and kill the cat. So the quantum mechanically, the situation of the radioactive material or radioactivity can be a superposition of two states, decay or not decay. But if the radioactive material decay, it kills the cat. So the state of the cat is either dead or alive, but quantum mechanically dead and alive. So that's what Schrödinger's cat is. So in quantum mechanics, you always have a two state or many state simultaneously that's allowed. But of course, cat can't be dead and alive. So it's a bit counterintuitive. And the same is happened for neutrinos. So we often call mu neutrino, because what mu neutrino, electron neutrino, tau neutrino, I said there are three neutrino states, because that's what we observe. So neutrino we observe are those state of electron or muon or tau neutrinos, but neutrino propagating in the space is different. Those are called neutrino 1 or neutrino 2 or neutrino 3. So it's a superposition. And mathematically, this means the neutrino flavor eigenstate is not a simultaneous eigenstate with Hamiltonian eigenstate, but that's not important now. So combining all these, what you can predict is that neutrino state is not conserved with time or with propagation. So here is example. So you create muon neutrinos, but through the propagation, this muon neutrino converted to electron neutrino, coming back to muon neutrino, and going back to electron neutrino again, you know, so you oscillate two state. So that is called the neutrino oscillation. And this neutrino oscillation is actually the evidence that neutrino have masses. Okay, so that's the topic of Nobel Prize 2015. And also, neutrino masses are the first clear evidence of the particle physics beyond the standard model. So that's why people think it's a big deal, and why neutrino is so exciting. Okay, so that's my kind of lengthy introduction, and I'm already spending half an hour, so how this goes. So now I'm talking, start my talk. All right. So now we know neutrino is, neutrinos go beyond the standard model. And by accepting neutrino has a mass, so there are so many new things. And I want to go through, but there are so many new parameters to measure. And the only way to know these parameters is by measurement. And at least the first three, Dirac CP phase, and the theta 2-3, and mass ordering of neutrino. So these are something we can measure, and we don't know yet. And the way to measure is a neutrino oscillation experiment. So there are another mystery, is a 4, 5, 6. So 4 and 5 and 6 are another mystery of neutrino. We need to measure it, but maybe not by oscillation experiments. So you have to have a different type of experiment to measure them. So page 17 is a formulation, so I maybe skip. And page 18 is the result. So how do you measure CP vibration with neutrinos? So this equation 2. Equation 2 shows it's an oscillation equation of neutrinos. Okay. And the second term is important one. The second term has a minus and a plus, and the minus for neutrino and the plus for anti-neutrino. So if there is a CP vibration, this term is non-zero. So the oscillation of neutrino and anti-neutrino are different. So if there's no CP vibration, this term is 0. So oscillation of neutrino and anti-neutrino are same. And we are focusing on this muon neutrino to electron neutrino. So basically, we want to compare muon neutrino to electron neutrino oscillation and muon anti-neutrino to electron anti-neutrino oscillation. Okay, and then the bottom figure shows how this oscillation looks like. So by assuming CP vibration is often quoted as an angle. So the 0 is 0. But if that is pi over 2 or minus pi over 2, you see the oscillation probability change like 25%. And if you switch to the anti-neutrino beam, again, oscillation probability change, but it's flipped. So if the CP vibration is delta pi over 2, probability is suppressed for neutrino, but enhanced for anti-neutrino. So basically, so if the CP is vibrated, you see the different oscillation than expected. So that's what you want to see. And experiment, so that's how experiment goes. So experiment, you measure it, yeah? So you create a neutrino beam, and then measure muon neutrino at the near side, and measure electron neutrino at the far side. And maybe electron and muon neutrino. So that's the measurement is. But you also need to simulate. So simulation side, you first simulate neutrino beam, neutrino flux at the near and far detector. And then you simulate neutrino interaction at the near and far detector. And finally, you simulate detector response, near and far detector, okay, with the oscillation formula, so that you can predict how neutrinos are detected in the far detector. And by comparing data and simulation, you can access to the oscillation parameter, because the oscillation parameter or oscillation formula is in your simulation. So by comparing with data, you can find if the neutrino violate CP symmetry or not. And experiment, so that's we are done in the T2K experiment. So that's this figure. Generate a neutrino beam at JPAC and sending this neutrino 300 kilometers away and observed at the Super-Kamiokande detector. So near detector located in the JPEG, and the Super-Kamiokande detector corresponds to the far detector. And you see this figure is, so 300 kilometer or 295 is pretty far away. So you have to penetrate your Earth. So this beam is going to the downward, basically. But that's something I want to explain next chapter. So now I'm starting to talk about the neutrino beam. So neutrino beam, so this is generated by at the JPEG, which is pretty close to the beach. You can see it. So the first stage, you are sending the proton. So your neutrino, you have to make neutrinos, and the proton means hydrogen. So you accelerate hydrogen atom using LINAC up to the 400 MeV. Then these protons are accelerated by RCS up to 3 GeV. Then these protons are sent to the main ring and accelerated up to 30 GeV. And finally, once proton reaches the enough energy, then the protons are extracted to the neutrino generation beamline and collide to the target. And the collision of the proton and the target makes neutrinos, and these neutrinos sent to Kamioka, 300 kilometers. So this is a more detail for the beamline. So the proton is it's coming with a pulse, and you see this pulse structure. So the proton beam is like I said, it's a pulse. It's not continuous, but it's coming with some sharp peak, which is important because we also use this timing structure for our analysis. And it's a picture of the beamline. So the center one is a ring. So this is a 30 GeV proton ring. And if you've never seen this accelerator, the pipe is actually quite small. And there's a reason, because if you want to accelerate a proton, you have to make it a vacuum. And it's not easy to make a vacuum of big volume, right? So the smaller pipe has an advantage, so easy to evacuate. So this 30 GeV proton pass through this ring and accelerate. And once you reach to the enough energy, you extract it to the another beamline and bend to hit the target, which is the left side. So this target is tricky part. So the target is made of graphite, and this target is located inside of the device. It's called a magnetic horn. And this horn is interesting because that's how you focus mesons. Okay, so let's see this cartoon. So proton beam collide the target, and this collision makes the mesons. And there are all kinds of mesons, but magnetic horn can focus either positive or negative mesons. So by doing this, you make neutrino beam, because neutrinos are made by decay of these mesons. So if you focus pi plus decay to muon neutrino, so you make muon neutrino beam. But if you change the current of this device, you can also focus pi minus. Then pi minus decay to anti-muon neutrinos. So by using this device, you can generate either neutrino beam or anti-neutrino beam. And this device is vital. So this device is broken, we are done for experiment. So it's a most important part for this neutrino beam generation, and we have 3 of them to make a really strong beam, horn 1, horn 2, horn 3. And all of them are separated with 1 meter concrete and 2 meter the iron block. The reason is because this area is very, very high radioactive. So it's not a human accessible area once you put the horn. And this picture is a horn 3 during the test. So the operation of this horn required high current, like a 250 kiloamp, to make 1.7 Tesla in this very short time, like a few microseconds. So it's a kind of extreme, and it makes a large noise. So I often explain this is the sound of a neutrino beam. So let's show you. So you see there's some sound hitting something. So that's the sound of the current. Because current is so strong, it vibrates by the Lorentz force, and that's what you can hear it. So that's how you make neutrino beam. And once you make neutrino mesons from the target, these mesons propagate the decay volume and makes neutrinos. And this propagates 300 kilometers away. This explains much other things, but I want to skip those things. So that's basically how you make neutrino beam. So we accumulate data from 2009 to 2018, and this bottom, the right plot shows how much data we accumulate, and the bottom plot shows predicted neutrino flux. And error is around 5%. So all of these are done by simulation we have. Okay, so now moving on detector. So going back to this figure, so neutrino are generated by the beam and propagate 300 kilometers to see by far detector. But you want to see the oscillation, so which means you want to compare neutrino at the 300 kilometers away and after the production, which is the 280 meters away. So we have a series of neutrino detectors in nearby, and these are called near detectors. There are two, one is in-grid and one is ND280, and I'll briefly explain all these. Okay, first of all, how do you see the neutrino? How this detector works? So most of them in the near detector are based on the scintillator. And the scintillator is a material, it's actually chemical, organic chemical. And the way we use is usually we mix with the plastic. So by mixing the scintillator material, so you can make a scintillator plastic. And when the charged particle pass through, they emit a weak amount of light. And these light are collected by the fiber and sent to the photon detector. So in this way, you can detect the tiny photon generated by charged particle, and you can see the trajectory of charged particle. Because we have an array of this plastic, and every time charged particle pass through, and of course this charged particle are the one generated by neutrinos. So because neutrino is invisible, right? So you don't see neutrino, but once neutrino makes the particle with a charge, the trajectory is monitored by this scintillator. So that's what you see from this bottom left. This is the data. So this array of the plastic, you see the dot, right? So each dot shows when this particle is detected. And the size of the dot is the amount of the energy dropped. So in this way, you monitor the trajectory of neutrinos. And we have this in-grid. Each one is like a 1 meter cube size. But we have 16 of them. So you put together, stack together like this way in the right side picture, so that you know the distribution of neutrino beam. So neutrino beam is not really focused because it's only the decay of meson. So it's like a shower. So we want to know how it looks like, the shape. And by in-grid, you can measure it. There's a bottom right plot. And we have a more detector in this area, but I skipped this one. And ND280. So ND280 is the other near detector, and it's pretty complicated. So maybe I want to skip this too. But it is important because ND280 is a very complicated neutrino detector, and it's designed to measure many different type of neutrino and also the many different type of interactions. So this picture shows, the bottom right. So bottom right is the one type of neutrino interaction which generate mu1, mu minus, and pi plus. Okay. And we accumulate a lot of these events. And that's the left side. It's a histogram. So this histogram The black is data, and histogram is a simulation. So this one shows how well we can predict our neutrino event in the near detector. And this information will be used because now you see the data and the simulation ratio is around 1. So it's pretty good. We simulate data pretty well. Well, actually, that's not true because our simulation is tuned. So our simulation is actually designed to reproduce this data. Because in neutrino physics, we still have so many unknown, like how neutrino interact has a big error. So we needed to tune using the near detector. So this is a very important element of our analysis. And we have 14 different type of interaction. So left one is CC1 pi, and the right side is when you don't generate pion, excuse me, which called CC0 pi. So we have many different these interactions and combine all of them for our analysis. I'm moving on the far side. So far side is the famous Hyper-Kamiokande detector, which won the Nobel Prize 2015. It's a 50 kiloton water Cherenkov detector. And inside of the tank has 11,000 of the big PMT, which I'm holding in the picture. And our detector is a smaller PMT. And the cable and all device located in the outer detector. So when you go inside of the tank, you work mostly in the outer detector. And in case you don't know PMT, let me describe quite quickly. So PMT, photon multiplier tube, is a fundamental device to see photons. So the way this works is it uses a photoelectric effect. So the photon generated by charged particle, which generated by neutrino interaction, hit the surface, and then it makes an electron by photoelectric effect. And these electrons are accelerated by this later stage because there's a voltage applied. So every time electron hit in a metallic plate, you are generating more electron, and in the end, you make a big pulse of the charge. So you see the big pulse from one photon. That's this device is doing, because the amount of photon produced by neutrino is quite weak. And the sensitivity of this PMT, 20-inch PMT, is incredible. So let's assume there is no atmosphere or anything. Let's assume there is no atmosphere. Then, by using this device, I can detect a tiny candle on the moon. So the amount of photon generated by a candle on the moon is enough to see by this device on the Earth. So that's the sensitivity of this photon device. Okay, and using this, you measure the neutrinos. So again, you don't see neutrinos. All you see is the charged leptons generated by neutrinos. So neutrino interact with the nucleus and makes the charged leptons. And these charged leptons make the Cherenkov radiation, and that's what we observed. And the Cherenkov radiation has a shape. It's a ring shape, but for the electron, this ring is fuzzy. And for muon, this ring is sharper. So by analyzing the shape of the ring, even you can tell it's electron, neutrino, or muon neutrino. So that's how we measure electron neutrino. Okay, and I skip this detailed background. All right, so that's a brief introduction of detector, and let's talk a little bit about interactions. So neutrino interact with the atom, or actually nucleus, and generating a charged lepton. This process is actually not well known. And not only the process is well known, you also need to estimate neutrino energies. That is also not easy, because you don't measure neutrinos. All you measure is a particle produced by neutrinos. So we use a theory to calculate how the neutrino energy is and how much this interaction happens. And this theory, I should go through this a bit quickly. So I'm talking with CCQ puzzle. So this theory has a big error. And Miniboom is one of the experiments to measure this kind of interactions. And we are working with a nuclear theorist more than 10 years for this. And the very recently, the 2019, the theory and the data more or less agree. So it's a very simple interaction. It's going back to here. So neutrino interact with the nucleus and makes charged electron. It sounds very simple, but because of nuclear physics, it is not simple. And only like last year, we came to the point, like a lot of theories, a lot of models, I have to say, more or less agree to predict this kind of process. And more specifically, we use this model, it's called the Valencia 2P2H in our simulation. So that's how neutrino makes charged electron, but if the neutrino makes more particle like a pion, it's more complicated, and I'll skip. So all nuclear physics is very complicated. And I go to page 43. So that's a summary. So you see this curve. So each curve is the interaction cross-section. So how likely this process happen with a function of neutrino energy. So top is neutrino interaction on carbon, and the bottom is anti-neutrino interact on carbon. And you see the size of the error bar. It's quite big. So the error is quite big, which means you can't measure neutrino so well. Well, that's why we have a near detector. So in principle, we measure this by near detector and using this information for far detector, because otherwise the error is too big. But neutrino interaction is a hot topic. So there are lots of materials, and that's something me and Pretam is also working. So I want to introduce this nustec a little bit. So nustec is an organization at Fermilab, and we promote this neutrino interaction physics, like organizing lots of events, like workshop and school. We had a school in 2015 at Japan, and I think I met Pretam first time I was there. So so that's a good way to meet people, and you can find more information from website. But also, you can find more information from Facebook or Twitter. So NuCrossSec, NUXSEC, NuCrossSec is our name. So please like it. But if you are more into this subject, go to this website and subscribe mailing list. Because mailing list, we also distribute all information such as workshop, school, and also online seminar. So you are connected, and you can learn the latest information about neutrino interaction physics. So, and also there's a past workshop we organized the last 2 years. Okay, now oscillation result. So we have a neutrino beam, we have a neutrino detector, and now we know how neutrino interact. So the first step is we measure neutrino interaction. The first step is using a neutrino data from other experiments, such as Miniboom, Minerva, Cyboom, K2K Minos. So these are other experiments. Why is that? Because these experiments tells you the precision of your neutrino interaction model. So by putting all together information from the world, you make a prediction of neutrino interaction. But as we discussed, the error is too big, so it's useless. What is important is the internal constraint, which means we measure all these processes in our near detector. So by doing this, you know what is the real error of each interaction type. So you can see this right side. So the right side is without and with near detector. So without near detector, the error of this mu neutrino measurement, let's say mu like ring measurement. So mu neutrino measurement has around 14.6% error, but by combining the data from near detector, this error becomes 5.1%. So you suppress systematic error significantly. So this is vital. So near detector information is extremely important for us to do a neutrino measurement at far detector. Okay. So the goal is to measure electron neutrino, because we measure mu neutrino to electron neutrino oscillation. So the error of electron neutrino measurement is kind of important. So we have a 8.8% error for electron neutrino measurement at far detector, and 7.1% for anti-electron neutrino measurement. So it's a 8%, 7% error, right? But at this moment, our statistical error is much bigger because we don't have so many events. So this 8.7% is it's okay. It's not a small. We want to make it smaller, but we can survive with this. And this is the page 48. So this is the data. So x-axis is the neutrino energy, and the y-axis is the number of the event you observed, and the top plot is the electron neutrino from a muon neutrino beam, and the bottom plot is positron from anti-electron neutrino beam. So you see not so many events. So this moment, electron neutrino data has a 75 event, and positron data has a 15 event. And we also have some special class of measurement, which I skip. So you see how data is higher than prediction. So this histogram is our prediction without assuming CP violation. But if there's a CP violation, the histogram becomes this dashed line, bit higher, which I agree with the data. And anti-neutrino, you can't see by eye, but we use, of course, the real analysis has a way more complicated statistical method. But the anti-neutrino, actually the prediction with CP violation also agree, which suppress the prediction. So it's not only data tells CP violation, it's also tell the value is. And the value we prefer is minus pi over 2. Because minus pi over 2 enhance oscillation from muon neutrino to electron neutrino and suppress muon anti-neutrino to electron anti-neutrino. So that's what we measured. And more precisely, page 49. So that's the value of delta CP with the error bar. So these are both shown with a two-dimensional space. So x-axis is a value of CP violation or delta CP, and the y-axis is other oscillation parameter. So this contour circle shows the size of error bar, and the location of the star is the most likely value. So we measure delta CP with some error, but in particle physics, you have to measure these with a 3 sigma, which is 99.7%. And the 3 sigma contour is shown with this bottom figure, the B. And in fact, this 3 sigma contour also include delta CP is 0. So that means statistically we are still consistent. There's no CP violation. So we need more data basically. So we need more data. That's why we have to upgrade. The first part is to enhance direction of neutral current by adding gadolinium in our water. So far, Super-Kamiokande measures charge lepton, but when the neutrino interact, you also produce nucleons, or you knock out, not really produce, but you knock, because you break up nucleus. So you produce proton and neutrons. And if you have gadolinium, the ion in the water, they can absorb neutrons and emit gamma ray. So basically, you can measure neutrons by Super-Kamiokande. And if I remember, I think Pretam's PhD thesis topic is related for this one.
Yeah.
So it's a pretty new things, and it's new. And 2 years ago, we opened Super-Kamiokande detector for this work. So before putting gadolinium, we want to fix the tank because this tank is already 20 years old. So we have to fix many things that happened 2 years ago. So now we are ready to put gadolinium. Meantime, we are trying to upgrade this near detector. So near detector is some people want to put a different type of detector, which I skip. But finally, we also have a plan to make a new tank, which is called Hyper-Kamiokande. So that's roughly 8 times bigger than Super-Kamiokande, and the construction started this year. So you see right side of the cartoon, it's from Higginson. So it's a pretty amazing track record, right? The first generation is called Kamiokande, 1983 started, and won the Nobel Prize 2002. The second one is Super Kamiokande, started in 1996 and won the Nobel Prize 2015. So now we are trying to make even bigger one, Hyper Kamiokande, and of course we expect the Nobel Prize sometime soon. These page 55 shows the performance of Hyper Kamiokande, but I skipped this. Page 56 is also performance of Hyper-Kamiokande. So Hyper-Kamiokande measures oscillation, so it studies delta CP or CP variation better, but also measure solar neutrino, proton decay, supernova neutrino, and many other things. So it's a very broad program. You can do many physics. Good, so that's end of my conclusion. So T2K is a neutrino oscillation experiment. We generate a neutrino beam at JPAC and observed by Super Kamiokande. And what we observe is we saw the enhancement of neutrino oscillation and we saw the suppression of anti-neutrino oscillation. So neutrino and anti-neutrino behave asymmetric way, and this indicates we have a negative CP variation phase, and this value we measured with quoted number. But we have a more plan for future, including SKGD, T2K upgrade, and Hyper-Kamiokande. So these are exciting. So that's my end of the talk, and I have a one slide. I don't know when is a good time, but maybe let's present now about the PhD in USA or Canada or Australia, because I thought this could be an interest for some of you. So let's talk now, and then I can answer all the questions together, either neutrino or PhD or whatever.
Okay.
So let's say you want to do PhD in USA. Okay. How this happen? So most important things is you apply. So if you don't apply, you don't get in. So don't just think. If you're interested, you must apply in the end. And why you want to apply? Because these are all free. So once you're accepted, you are fully funded. So no tuition fee and living cost is paid. Deadline of application is usually end of the year, so around December this year to January of next year for the next year admission. So if you're interested to go PhD next year in USA, you should start now. And the last point is student from Bangladesh is rare. And actually this is important because this PhD in USA, they try not to have too many students from one country. And they always have so many applicants from India and China. So applicant from Bangladesh is rare. So you have some advantage to apply it. And then there's the list what you need. So first is you need application. And application process is different for each university. So you have to check one by one. But if you go Google and type MIT physics, PhD admission, and then you get some information. So in this way, you can find all the information. The things you need is a personal statement. And a personal statement is you have to mention how you like science, but it's more importantly your research experience or maybe good experience in general. Okay. And the second one is the reference letter. This hopefully from your project supervisor. So research experiment is important. That's what this shows. You need a reasonably good score for TOEFL and a reasonably good in like high school level. So you don't have to be advanced level, but at least you can understand and speak high school level English. You need a GRE score, but this is changing. So I think you shouldn't focus too much for GRE because it's too expensive, and these days many universities don't require GRE scores. So it's other exams. And you need some official transcript from university and degree from undergrad. You don't need a master degree. And you have to be good at physics reasonably. And the application, you have to emphasize anything you want to emphasize, some skill, ability, etc. And you have a question, just send me email. Okay,
thank you.
That's all.
Okay, thank you, sir, for your wonderful presentation. And also thank you about the information of the youth scholarship and admission process. So now we can start our discussion. If you allow me, then I can ask the audience. So, dear student and colleagues and the audience, you can ask question now because the discussion session has already started. And if you want to join live, then please SMS me. I can send you the link. So is it okay now? Hello? Can you hear me now?
Yeah?
My audio is okay now? Or problem?
Yeah, it's not easy to hear, so I think it's better if I can read the question.
Okay. Then
Is that, can I do that?
so I think my line is not enough to connect. So maybe sound is so let's check the comment. Is there any question or not? So we haven't got any question yet.
Yeah, you can ask question later, or I can share slides too. So
Okay, I think is it okay now for my sound is okay or problem? Okay, maybe no, there is no question yet. There. Okay, then I think we should stop because I have two questions. One, so we have a water Cherenkov detector and scintillation detector. So which one is better? If we
so scintillator is better to see the detail, because now you see all track, so you can measure not just lepton but pion or maybe even proton. so you can study all the detail. Cherenkov is better because it's cheap, so you can make a really big detector. So in terms of far detector, the water Cherenkov is only option because you need a big detector.
Okay, thank you. So another question. So sometimes you can see that we have a neutrino from reactor. So can we use neutrino as a reactor monitoring? Can we use neutrino as a reactor monitoring to monitor the reactor?
It's a very active field. People are working on, and it's yes, and there are lots of detector already, and many neutrino detector is in research reactor. Because there's a few issues, because these detector are, if you want to see neutrinos, you have to be very close. So it's very close to the core, but a lot of detector is made by a liquid scintillator. So it's not a plastic, but a liquid scintillator. And the liquid scintillator is oil. So it's burn. So it's a bit dangerous. So you don't want to be too close to the reactor. So theoretically you can monitor, but this moment we don't have a realistic detector design for this.
Okay. So I have a question. I got a question from one of my students. She asked that what happened neutrino and antineutrino diagram? Her question is, what happened? It's time to take up from zero. What happened? Neutrino and antineutrino diagram.
Hi. I don't understand. What the time take up mean?
I also do not understand exact question. Okay.
Time take up from zero.
So this broadcast actually maybe will share in the Facebook. So if somebody asks question, then we can discuss later. I think that will be better.
Sure,
And I want to thank you again because we are too busy, and you give me the time to talk with us actually. And this is very important topic nowadays, because if we know neutrino better, because if we can understand the supernova, and maybe in near future there will be another supernova explosion. So yes, this is very important topics, and I hope our students have already came to know what is neutrino and their oscillation by your presentation. So I think there is another question from, so when particle and antiparticle combine together, then it disappear. How can it detect it?
Wait, say that again. When the particle and antiparticle combine together, then disappear. How can it? Yeah, well, it's not disappear completely because
Decomposition.
Yeah, so energy leave, and the most common way is emission of 2 gamma.
Yeah.
So you can see those to find it.
Okay. Then, yeah, maybe we have a time. We keep our discussion about 15 minutes, but still we do not have much question, so we can stop it now. So I want to thank you again. So thank you, sir, and you really give us time so that actually the student of our university, not only our university, because all the students who are watching this telecast actually get benefited from this presentation. And I want to thank you again for your last slide, because we have also explained the admission process and the scholarship process in USA. So, okay, so I think the question, you can check the question. My question is that if you time up to zero, what's the difference between neutrino and antineutrino diagram?
I still don't understand. What's a time up to zero mean?
I also do not. Okay, let's. We can. I can ask her later, and then
Yeah,
I will ask.
ask me later. It's fine.
So thank you again.
All
So now
right.
we can. Yeah. Uh, bye. Let's
Thank
say
you.
bye. Bye. Bye.
Bye.
Thanks a lot.